Testing. This is the second presentation we're testing. This is under full screen. So under full screen, let me bring up this growth, reviewing some of the calculation used for valuing returns. So this is the basic equation we use to basically look at the value. So we're more interested in growth rate. So R here represents the growth rate, N here represents the time period of the return based on the growth rate. So you have the principal amount and the value as a result. So for instance, if you have a 100% growth rate, R would be 1. So that would be 1 plus 1, essentially 2 raised to the power for the number of years. So after 1 year, n equals 1, that would make this essentially 2 times the principal. So the value is equal to 2 times the principal. If you were to back out the equation, you'll have essentially value divided by principal equals 1 plus the return raised to that power. And of course, if you were to essentially do the 1 over n of the value of the principal, you essentially get 1 plus the rate of return, or essentially the rate of return will be based off the value and divided by principal raised to the 1 over n minus 1. So here is essentially the column of essentially years, n. Here is the value of the basic value divided by principal from this equation here. And these are essentially the rate of returns. So for instance, generally we look at doubling. So to double in 1 year, as I just pointed out, that would be essentially 100% return. So the rate of return is 100. There is a rule of 72, which I will review here. And the rule of 72 states that the rule of 72 is that the investment will double for growth rate times the number of year equals 72. i.e., for an 8% growth rate, it would take 9 years, essentially 8 times 9 equals 72, to double the initial investment. So let's go take a look at the growth rate plot again, the growth rate calculation. So here's 9 years, and here's the doubling, and it says 8%, which turns out just right. Now if you reverse that to essentially 8 years, it should be about 9%. So again, almost 9%. So the rules of 72 works out quite nicely. So if you look a little further here, I have the rule of 72 located here. So you can see the equation 72 divided by essentially the number of year and divided by 100 to get percentage. So again, these two should match up very nicely if that's the case. And you can see here they match up very nicely up until you get to about 4 years or under. You can see it starts to deviate more as you go under 4 years. You get 19% versus 18, 26 versus 24, and then it starts to deviate quite significantly as you get under the 3-year mark. But otherwise, it's very close. So the rules of 72 applies very well to do a quick analysis on the rate of return. And you can see here, I've actually created the value versus principal. So whatever the value you're looking at, like the current value divided by the initial investment, you can get an idea based on the number you've held what the return rates are. So for instance, if you actually got the value divided by principal of possibly 1.5, so 50% return, this will be your 50% return spot. And if you look at, say, it took you 6 years to get there, you can see 6 years will get you a 7% annual return rate. And if you did it in 30 years, well, you're only getting essentially 1.4% return rate. So the longer it takes you, of course, to get to the 50% rate, you are essentially getting less return per year. So this is a nice table to quickly determine your return rate and how much you're actually getting for your investment. We'll use this in the future, so keep this in mind. Here's a second calculation I use to basically do a linear regression as well as an exponential regression, which is a log regression on stocks earning. So for instance, you're given the years and you're given the earnings per share. So you can see at $2.50 for 2010 to 2017 of 5.9 for IBM, you basically get essentially the actual growth to the best fit for exponential and for linear. If you're looking at growth rate per year, usually you look at an exponential growth. So if you look at the exponential growth here, the exponent is essentially the linear fit of the data, best fit, and the value is 0.1261. That represents essentially 12.61% growth rate per year. If you look at the linear fit, you can look at the component next to the x, and it is 0.5054. So for every year, you basically have 50 cents increase. So because linear fit usually doesn't work very well for something that should be consistent and growing every year, I tend less to use it. However, in some cases, it just indicates a company is not growing very fast, so you might want to use this for a slow growing thing. And you can see here that says about 50 cents, 50.5 cents growth per year. And you can see here that's 40 cents. Here to here is 60 cents, so you have 40 cents, 60 cents, 40 cents, 55 cents, 75 cents, 50 cents, 40 cents. So for this, it does look like a linear fit might be better. But in general, you're looking for exponential growth, and you should be looking for the exponent to the coefficient of the x. Same thing as the coefficient to the x here. However, here gives you an exponential growth rate, which is what you're usually more concerned with. Okay, that's it for growth rate. And be sure to go ahead and use this chart to identify your growth rate. Again, you want to look at, say, a final value point to the initial value point, and determined by the number of periods or years. And by using these two, you can get roughly your rate of return. Thank you.